Another beautiful day in the neighborhood. Happy second to last Wednesday class that we have together. How precious. So, logistics updates. Reminder to y'all, student perception of instructor means a lot to me if you fill that out. There is no tangible benefits on your end, but I appreciate it. So, just a reminder to y'all, very much appreciate it if you can fill that out for me so I can give feedback so I can do better. Otherwise, I don't think there's too much to say. I think I told y'all last time, so the grader again, hopefully in the next couple of days I'll hear from him. I'll let you know when I know. But I think I told y'all he was 2/3 of the way done as of Monday. So he should finish the last third hopefully by the end of this week. And those will be the pre-response grades. And once I receive those, I'll need 24 hours to process them. So, great. All right, so last class, we introduced the most complicated thing in rotational stuff, moment of inertia. Moment of inertia is the most complicated thing. So if it made sense, I say that, not to say moment of inertia is awful, but to say that if it made sense, awesome. If it didn't make sense, it's the most complicated thing. So moment of inertia we talked about. Moment of inertia was like mass. It was for rotational motion, moment of inertia is like mass. Specifically, if something has a lot of mass, it's hard to accelerate. If something has a lot of moment of inertia, it's hard to angularly accelerate. Whether that means you make it spin faster or whether that means you make it spin slower. If something has a large moment of inertia, it's going to want to keep doing what it's doing, whatever that may be. Whether that's not spinning or whether that's spinning really fast, it's going to want to keep doing that. To change it will be more difficult. If it has a low moment of inertia, it's easier. And that all had to do with how the mass is distributed. Remember, moment of inertia, it was basically an integral of mr squared, how the mass was distributed across, r squared dm. How the mass is distributed. The farther away it is, kind of the harder it is to change what it's doing. Why? Because remember, y'all, the farther away it is, it will have a higher tangential velocity. And if it has a higher tangential velocity, it has a higher momentum. And if it has a higher momentum, it's hard to change something's momentum. So again, it all connects together. But that's the rationale. The farther away something is, the faster its tangential velocity will be. Therefore, the harder it is to change its momentum. And then bring it back, harder to change its angular momentum. Okay, so we introduced that. We basically spent the entire last class just talking about moment of inertia. I gave you all this sweet chart of a bunch of them, and I said you do not need to memorize any of these. You do not need to have any of these memorized. If you need these values, if you need the moment of inertia for a sphere about the center, if you need the moment of inertia of a disk or a hoop or anything, I will give it to you. Okay? So there's some peace of mind there. If you need it, I will give these to you. You should not need anything memorized in this class. That's not the point. Physics, engineering, it's not about memorization. It is handy to have certain things kind of off the top of your head. It is handy to know that gravity is negative 9.8 meters per second squared. It is certainly like knowing the units. That's pretty important. Being able to do unit conversions quickly, that's just a very useful handy skill. It's like being able to multiply 2 times 3 in your head. It's one of those things you don't necessarily have to be able to do it, but it makes your life a lot easier if you can. What I ended with was the parallel axis theorem, which said, hey, if we know the moment of inertia about some axis, if we just shift that axis, we can easily calculate the new moment of inertia. Really, really cool tool that you can use. Really, really simple. And so we're going to practice that today. So we did an example of that, a clicker question example, where we took a sphere that had a moment of inertia. A sphere about the center is 2/5 mr squared. To make it more clear, just to make certain we don't do anything silly, this is 2/5 times mr squared. That mr squared is not in the denominator. We shifted it over by r, so we just added mr squared, and we got our new moment of inertia, and it was great. We had so much fun. So much fun, we want to do it again. There it is. Using the parallel axis theorem, what is the moment of inertia of a rod of mass m about the axis shown below? So I have a rod here that is spinning. Its axis of rotation is located L over 6, the length of the rod divided by 6, away from the end. So what is the moment of inertia of this thing? So the moment of inertia of a rod, so if the axis of rotation was instead dead through the center, right through the center. If it was spinning about the center instead, its moment of inertia would be, so if it was about the center, it'd be 1 over 12 ml squared. So we want to find the new moment of inertia. I guess you can kind of do the whole classic givens missing, all that kind of jazz. I'll write it out that way because it's just nice and organized. So we have our original, I'll call it I naught, 1/12 ml squared. We are trying to find our new moment of inertia. I don't know, we'll just call that I1. It's the new one. And how are we going to do this? It tells you what to do in this problem. How kind of it. I will not probably be as kind in a problem I give you. You will have to know to use this theorem. But yeah, if the axis shifts, if I give you it about the center and it shifts, the new moment of inertia is going to be the original moment of inertia plus md squared, where d is the distance it shifted. And this is where I will pause and I say, figure out how much it shifted and see if y'all can come up with an answer. The answer in the problem set is in a fraction form, and I'll probably show that, but the reality is I don't need you all to necessarily do least common denominator, all that. I'll put it both as a fraction and as a decimal. You'll see what I mean. But for now, see if y'all can figure it out. How far did it shift? What is that distance? Place D with that and see if you can figure it out. So I1 will be, and again, I'm not going to solve it at this point. What's that D going to be? That's the question for you. I'll fill that in a second. Now, very important here, L is exactly what it sounds like. It's the length of the rod. It's the length of the rod, not the radius. This L is the length of the rod, not the radius. So that's purposeful that we use L and not R. And you can kind of see that in the picture as well. So whatever you say it shifts needs to be in terms of L. All right, I think that's enough thinking time. So how much did it shift? It shifted 2L over 6. And I'll go ahead and show you all where that came from. It shifted 2L over 6. There wasn't any math. Okay, maybe I kind of did some math in my head. Why is it 2L over 6? Well, let's just think about the original. And I could have written, so 2L over 6, that's the same as L over 3. If you want to write it that way, that's also cool. Where was it originally located? Where was it originally located? It was located halfway through. Where was the original axis of rotation? It was some distance L over 2 from the end. That's where it was at. The original axis of rotation was some distance L over 2 from the end. It's halfway. This whole thing is L. So it was originally L over 2. So, at the end of the day, again, I've kind of already labeled it here. I'm trying to find this. If this is L over 6, then this is going to be 2L over 6. Because what's L over 2 equal to? L over 2 is equal to 3L over 6. If you do 3L over 6 minus L over 6, it's 2L over 6. All right, a lot of this, if this is confusing, this is going to be one of those just kind of sit down and look at kind of situations, looked out. This is very important that you all can identify that this is 2L over 6, that it's shifted. And it's nothing crazy. It's just like this is a spatial reasoning skill. There's no physics I'm doing here. Figuring out that it shifted over 2L over 6, there's no physics to fit. That's spatial reasoning. So to that end, this may be, if that's not clear why that is, that may be worth spending some time. I guess I can also, if that's L over 6, that's also L over 6. So if this distance is L over 6, this distance is L over 6, this distance is L over 6. So shifted 2L over 6. Anyway, spend some time on that. That's a very important skill. So if that doesn't make sense, that is going to be one of those. Kind of go back, look at, think. To that end, it shifted 2L over 6. And at this point, you can put 2L over 6 or L over 3. It doesn't matter. It's all going to end up the same. But I put the 2L over 6 because it's a little easier to see that than if I told you it was L over 3. Whatever. Cool. What do you do now? You just add those numbers together. Okay, well, we got to do one step first. Let me give myself some space. So that's the challenge to these problems. Literally, the challenge is recognizing, 1, that the axis shifted. 2, how much did it shift? If you can do those 2 things, you can solve these problems. Boom, I just need a little bit more space. We'll put the picture back in there as well. Yeah, afraid that. Send you to back. Beautiful. Line everything up all pretty. Look at that. All right. So now you just do some math. I'll do it both ways. I'll do at least common denominator, and I'll do it. So my new moment of inertia is 1 over 12 ml squared plus m. I need to square the inside, so that's 4l squared over 36. Let's go ahead and just rewrite that. 1 over 12 ml squared plus 4 over 36. I'm going to go ahead and simplify that to 1 over... I'm not going to simplify it. You're going to see why. Let's leave it as 4 over 36. You may immediately be like, but 4 and 36, I could simplify it. You'll just end up you'll have to do it backwards again. All right, least common denominator is 36. So I change this first one to 3 over 36 ml squared plus 4 over 36 ml squared. Now you can add fractions. And it's 7 over 36 ml squared. Boom. Final answer. Bada bing, bada boom. This last step of doing least common denominator, I'm not super worried about whether you can do that. Like, yes, you should be able to do least common denominator. Is it worth the time and energy? So the reality is, when I give you all a question like this, how can you do this problem instead? A calculator, a fraction is just a division problem that hasn't been solved yet. So 1 over 12 is 0.0833 ml squared. That is not going to be enough room. 0.0833 ml squared plus 4 divided by 36 is 0.111111. I'm just going to do 3 of them. That's good enough. Yeah, let's throw an extra one in there. So what's my total? 0.194 ml squared. Those are the exact same answer. Do 7 divided by 36. Oh, look at that. I get the same answer. So, both of those are acceptable. If you don't want to deal with the least common denominator stuff, that is just as valid. They mean the exact same thing. So again, just to recap, what did we do here? The axis shifted. We had to figure out how much it shifted. We plugged that where D is and did math. So great problem to look at. This problem's so good, we're going to do it again in a different way. Okay, so this is one way to calculate moment of inertia. If you already have moment of inertia, figure out how much the axis shifts. Cool. What's the other way? Calculus. How can we find the moment of inertia of this rod? Integrals. This is the only type of moment. This specific problem, a one-dimensional rod, is the only type of moment of inertia I can actually have you calculate with calculus, because it's a single integral. If this object is one-dimensional, so you need only a single integral. If it was two-dimensional, you need a double integral. Three-dimensional, you need a triple integral. You have not learned double or triple integrals, meaning you are blessed to only have to solve the moment of inertia for a one-dimensional rod. So, how do we do that? The integral is r squared dm. Here's the problem. Where my mass is located is dependent upon r. They are correlated. So we have to take this dm and we have to change it in terms of the length. Lambda dl, which we could instead call kind of lambda dr. Lambda dl. So we replace, and again, we can kind of just call that LR in this case. You'll see why in a second. So we replace that dm with that lambda dl. We're just going to go ahead and switch that L to an R. What's going to be funky here is this R is not going to be, well, it is going to be R. No, that's fine. It is going to be R. So there you go. We're going to kind of sub that in. Instead of an L, we're going to put an R. Why is it lambda dl? So lambda is density. Lambda is one-dimensional density. So it's mass divided by, in this case, length. Lambda is one-dimensional density. Two-dimensional density is sigma, is mass over area. Three-dimensional density, that's the one that you are the most familiar with, is mass over volume. Turns out there's three types of densities depending on the dimensionality of your problem. Does this matter? Yes. I am not going to necessarily quiz you on this, but this is something you all should have tucked somewhere into your head. When you get into Physics 2, this is going to come up. At some point, just remember that there's three types of densities. When you get to Physics 2, this will come up. Oh, the last update. People keep asking me if I'm teaching 2049 in the fall. I still don't know. But I emailed the chair and just said, hey, if the opportunity arises, let me. Like, I am interested in teaching 2049 in the fall. And so he said, I'll see. So anyway, I told you I checked. That's where we're at. Keep you all updated with exactly what I know in that category. What I know at this point is the chair knows I'm interested. If an opportunity arises, he will tell me. So, there you go. There you go. So exciting. Does it mean anything?
No.
I don't know. Yeah, I don't know. All right, so let's do this, the exact same problem. It was so much fun. Let's do it another way. We already know what the answer is going to be, so we can check our work. So we said the moment of inertia is going to equal lambda, the integral of r squared dr. And here's where you have to be clever. Here's where you have to be clever. So if you multiply the radius times the lambda, yeah, you get the mass. Choosing our limits of integration. That's what we have to be considerate of here. And how are we going to choose our limits of integration? We have to choose where 0 is. Let's make this 0. Let's make this 0. That's my axis of rotation. Because why are we going to make that 0? The moment of inertia of a mass at that spot is 0. So we're going to choose that to be 0, which means This side is to the left of that, so it's negative L over 6. This side is to the right of that, positive 5L over 6. This is our limits of integration. Go ahead and try it, y'all. Do an integral. R squared dr, really easy integral. Give you all a few moments to do this. I believe in your abilities to integrate this. So you should have gotten lambda r cubed over 3 from negative L over 6 to positive 5L over 6. Now you just plug them in. So let's just pull that lambda out. Let's go ahead and pull that 3 out. And pull that L cubed out as well. When you plug it in, the L's for R. Here, that may be too much. 5L over 6 cubed minus negative L over 6 cubed equals, so y'all can see the L is going to get cubed in both of them, so I can pull that out. I don't want to keep writing it. Lambda L cubed over 3. 5 cubed is 125, divided by 6 cubed is no idea. 216 minus plus subtracting a negative 1 over 216. So at this point, the hard part was setting up the integral. At this point, it's just doing an integral. Depends, maybe. It depends. Depends who you have. Yeah, the question was, are you going to have to set up integrals in physics too? Depends. I could very likely yes for some things. Well, you have to set up integrals that are, there's really tricky ones, and then there's not as tricky ones. It'll depend on who you get. As far as how much they expect. Anywho, 126 over 216. And you may be like, remember, this is our end goal. Our final answer should be 7 over 36 ml squared. We are not there yet, but trust me. I'm going to show you these are the same answer. Just got a little bit more to do. All right, so what more do we have to do? We are almost there, but I ran out of space. Trust me, it's just going to be a couple more steps and we're good to go. Take the picture and put it over here. All right, so what do we have left? Equals 126 and 216 share a multiple. My calculator died. Let's see. One of the things we can look at is we can see 126 is obviously divisible by 2, so that's an easy one to identify, and you can kind of go down the ladder there. You can also see that 126 is divisible by 3. This is just kind of good, handy things to be able to figure out. How do you know that 126 is divisible by 3? 12 is divided by 3, and 6 is divided by 3. So you don't get any kind of weird leftovers. So that's an easy way to figure that out. Let's see if they're both divisible by 12. Sometimes these least common denominator things, it's just a matter of trying things out. So, let's see. 6, awesome. 216 divided by 6, awesome. Alright, turns out both these are divisible by 2 and they're divisible by 3, which means they're divisible by 6. I'm going to do this the long way and then show you all what I would probably just do instead if this is me. Alright, so this is 21 over 216 divided by 6 is 36. Those are also divisible by 3 again. This seems involved, but this is how I look, I don't have a bunch of crazy factors in my head memorized. These are each divisible by 3, so that's 7 over 12. Oh my gosh, it's all coming together, y'all. 7 over 36 lambda L squared, or cubed. And you look at this and say, that's not the same. Pull one of those L's out. This is the mass. Lambda times the length is the mass. We did it! Yay, calculus! Yay, derivations! This is how you calculate moment of inertia, and this is the easiest case. One-dimensional. Yeah, that's a good question. So that last step, I pulled out now, lambda times L, that is mass. Lambda density times length, linear density times length is the total mass. So, looked like a lot of steps. This is a nice window into your future. When you all get to later engineering courses. So, in Physics 1 and Physics 2, no, the math should not take a lot of your paper. But as you get further into your classes, the math is going to start to take over. Because the problems get more complex. More complexity means more steps means more calculations means your paper, one problem may take an entire sheet of paper. And that's okay. But we build to that experience. So in physics, at least I can speak to that. In physics, as a physics major, yeah, by the time you get to upper level undergrad courses, junior, senior year, it is not uncommon for a problem to take an entire sheet of paper. Maybe just a front. You all, when you take statics, you're going to have systems of equations. It's going to be great. So for now, I am teaching you all a bunch of different topics and trying to give you a conceptual understanding. Your later engineering class is going to be applying those to specific situations and new equations. And yeah, it's going to get mathier. So you all signed up for it. You have to speak the language. I mean, it's like, so this is the language that you all need to speak very well. Math. It is a language. It's the language of logic. Think of it, you start out as an English major. You know, when you all started speaking English in the beginning, you know, when you started writing stuff out, you started with a word, and then a sentence, and then a paragraph, and then an essay. You all we start small, and as time goes on, you're going to be writing essays and math. And all the stuff will mean things. That's what's cool about it, though. It means stuff, and you'll show it to people, and they'll say, that looks terrible. But you, hopefully, if you understand what you're doing, it will mean something. Your essay will have a meaning to it that you can interpret and someone else can interpret, and it's fun. It may not sound fun, but it's fun. This is why you all need to find people to do this work with. Every single time you take a step in a math problem is a chance to make a silly mistake. If you do this work, there's a reason people do this work together. There's a reason people there's groups and stuff like that. There's a reason they double check each other's work. Because the beautiful thing is there's one final answer. One right answer. So if you and your friend are solving a problem and you both get two different answers, either you're both wrong or only one of you is wrong. But there's a guarantee at least one of you is wrong. At least. Having someone else there will save you a lot of pain and suffering. Also pro strat, when you get to that point, sometimes you step away from it because at some point it all starts to blend together and look like spaghetti. And you have to take a step back for your brain to look at it fresh. So, anyway, I say this. For now, don't worry about it, but just know it'll happen. And it'll be fun. It'll be great. And you'll love it because you're going to be around other people that also love it. And it's going to be a great time. Okay, so, great. Moment of inertia. We're finally done with it. I say done with it. We're done with learning how to calculate it. Now let's use it. Now let's actually apply it. What do we use it for? Rotational kinetic energy. What do we use it for? Calculating angular acceleration. What do we use it for? Angular momentum. Basically, all the things that you use mass for. What did you use mass for? Kinetic energy. What did you use mass for? Finding the F equals ma, finding acceleration. What did you use mass for? Momentum. Just put the word angular in front of all of those, / rotational, and you got the rotational equivalent. So, one step at a time. All right. I'm not going to even say anything about this. I'm so tempted to, but I'm not going to. Which will reach the ground first? A 5 kilogram block sliding frictionless down a ramp, or a 5 kilogram sphere rolling without slipping down the same ramp? Which will reach the ground first? I will clarify this 5 kilogram sphere, for it to roll without slipping, there has to be some friction for it to grip. Something cannot roll without friction. Easy example, a car on ice is not going to go anywhere. Oh, it can spin, but it's not going to move anywhere. So the without slipping does mean that there is some friction for the sphere. There is no friction for the block. But note that the sphere is not sliding. It is rolling down. It is rolling down. Let's see what these answers look like. I'm curious. Nice. Love it. And the reason I love it is most people are getting it wrong. That's purposeful. All right, I'll give you all 10 more seconds. Yeah, second guess yourself, everyone. No. You'll see why. I'll explain. Remember, there's not much of a penalty to missing these things. All right, we'll close it out in 5, 4, 3, 2, 1. Boom. Which one will reach the ground first? You're going to hate this. It's the block. And you're like, but what? But wheels! Wheels are better. Yeah, okay, they are for most things. But yeah, also how often do you all run into frictionless surfaces? So the frictionless kind of throws thing off here. The natural question is why? Why?
So let's say the sphere's on the frictionless surface.
Fun fact, if this sphere was on a frictionless ramp, so the question was, what if it was on a frictionless ramp? It would just slide down and they would reach the bottom at the same time. Yep.
Even with the inertia thing that we were talking about?
Yeah, it wouldn't matter. It wouldn't spin.
It wouldn't spin.
Yeah, that's a great question. So if in both cases there was no friction, they would reach the bottom at the same time, because the sphere wouldn't roll. Why should it? It's just going to slide down the hill. The only reason the sphere rolls is because the friction catches the bottom, and then it rotates. And then rotates. There's no reason for anything to roll if there's no friction.
It's kind of like when you drop something in a vacuum, like a feather.
This is more, yeah, so that's, if this was a 10 kilogram sphere, it would also reach the bottom at the same time. The reason why something rolls is friction applies a torque to the bottom of a sphere. So gravity wants this thing to go down the hill. Torque applies there's a torque here, causes it to roll. All right, why? Why does the block get to the bottom? Because there's an energy associated with rolling. So for now, I'm going to introduce this energy, and then we'll go back and look at the other problem. There is an energy associated with rolling. There is an energy associated with the rotating object. Something could be, that's kind of silly. I could spin a tire in the air, and even though it's not moving left to right, it has energy associated with it. How do you know it has energy associated with it? It can do work. Something that's spinning, you can imagine all sorts of applications for something that's spinning. How you can take that energy that's stored in the spinning object and convert it to something else. That's all energy is. Is it some kind of thing that I can change to some other kind of energy? Something I can do work with. So here's the equation for it. It should look a heck of a lot like kinetic energy, like regular. Instead of 1/2 m, so regular kinetic energy is 1/2 mv squared. Replace m with moment of inertia, replace v with angular velocity, and bam, you got rotational. Same idea. You can see, so we needed moment of inertia for this. It's joules, it's energy, y'all. Who cares? If it's energy, it's joules. Kinetic energy, joules. Rotational kinetic energy, joules. Potential energy, joules. Thermal energy, joules. Electromagnetic energy, joules. If it's energy, it's joules. That's what's so special about energy. It's all the same thing, just converted from one form to another. Okay. So, why does the block reach the bottom first? Well, it's because of conservation of energy. Conservation of energy. So let's see if this plays into this one. No. All right, so let's go back to this. So let's draw that situation. I have the block here. I have the sphere here. They both end at the bottom. Conservation of energy, y'all. The energy I start with must equal the energy I end with. That's always true. We're assuming no friction. So something that's nice about something rolling is even though there's friction, it doesn't lose energy. Funky. Even if something's rolling, it doesn't lose energy to friction. That's why it's nice. Let's call this an H. It starts at some height, H. They both start at the same height. I'll give myself a little bit of space. They both start at the same height, H. This is a good review, y'all. I want you to see if you can set up conservation of energy. What energy do I start with? What energy do I end with? At the bottom, they are moving. Now, they couldn't reach the bottom if they weren't moving at the bottom. So try to set up conservation of energy, y'all. Both of them only start with potential energy. They both start with the same energy. Exact same. Potential energy doesn't care what the object looks like. There is no kinetic energy in the beginning. There is no angular kinetic energy in the beginning. There is no elastic potential energy in the beginning. There is just gravitational potential. So now you all have 4 types of energy we've talked about. This is the 4th one. And the question is, what energies do they end with? The block ends with only kinetic energy. The sphere ends with kinetic energy and rotational energy. Why does that matter? I'm just going to completely make up numbers. Let's say they both start with 10 joules. This one starts with 10 joules. This one starts with 10 joules. That means at the end, all my potential went to kinetic. All my potential went to velocity. All of it. It went all from potential, all to kinetic. Here on the bottom, who knows what exactly the ratio is? It doesn't matter what the ratio is. Let's just say a lot of it went to kinetic. Some of it goes to rotational. So if we compare these, this one's velocity, the sphere will have a smaller velocity than the block. If it has a smaller velocity, it took longer to get there. It's traveling slower. Things that travel slow take longer to get somewhere. So, what does this say? Why does this matter? Things that rotate, that some of that energy got converted to rotation. So that's just interesting, y'all. It's not what you expect. When something rolls down a hill, some of the energy is lost. I say lost. Some of the energy is converted to the rotational motion. That can be beneficial. It all depends, y'all. This is not a bad or a good thing. It all depends. Yeah?
So I should be careful not to associate this with friction.
If friction's involved and I ask this question, you would have to do a bunch of math to figure out which one would actually reach the bottom first. It would depend upon the coefficient of friction. It would depend upon the mass. So if friction existed, this problem becomes a lot more complicated because you'd actually have to do the numbers. to determine which one reaches the bottom. Even if there was friction, the box could still win.
What I'm saying is, like, because the ball is long, there is some sort of friction.
Yeah. But even so, what's nice? So the question was, kind of, why didn't we account for the energy lost to friction? I think maybe.
Yeah, like that energy right there.
Yeah. So a rotating body, if it's not slipping, doesn't lose any energy to friction, which is nice. So that's an important distinction to make here. A rotating body does not lose energy to friction. I mean, technically, probably, if it's not slipping. If it's not slipping, it doesn't lose any energy to friction. That's why wheels are great. That's why wheels are so efficient. Friction doesn't slow them if they're not slipping. The reality is, everything slips a little bit. Everything slips a little bit. Maybe really hard to tell. But even when you're walking, your shoe kind of slips a little bit when you're walking. Like, everything slips a little bit. Nothing is completely rigid like that. So, even if there's no air, an object that's rolling on the floor, it'll go a really far distance, but it will eventually stop because it is slipping just a tiny bit. But in an ideal world, if it wasn't slipping, it'd roll forever and ever and ever and ever and ever and ever and ever. Even if there's friction. So, yeah, interesting things, y'all. What's the takeaway from this? When you're doing conservation of energy, you now need to account for rotating bodies. Because some of the energy will go to that rotation. That's the major takeaway. What's really cool about this? We didn't need to know anything about the friction of this surface. You didn't need to know anything about the path this surface takes. Remember, energy, y'all, is so powerful as a tool. I showed you all that this ramp was straight down. The answer would have been the same if it was all wiggly waggly. The exact same answer if this thing was instead a crazy path like this, and this one had a crazy path like this, wouldn't matter. Which is cool. Well, no, it would. It's stupid. Nah, it stinks. It wouldn't matter. The final velocity wouldn't matter. The final velocity wouldn't matter. It would take more or less time, which is a whole thing. But the final velocity wouldn't matter, which is maybe what you care about more so. Yeah.
It's because you relate conservation of energy and whether it worked in that equation, it didn't really matter what the path.
So the path doesn't matter if only you care about the beginning and the end, and if you only care about the variables in this equation. One thing I can't say though, which I did just say but I was wrong, the time it takes is more complicated. Because if the path is all crazy, the velocity is going to change over time, and you actually have to do an integral to calculate the time it takes to go down it. That's a whole thing. It's feel free to look that up. What's the ideal path for something to go down to reach the bottom the quickest if you have a ramp? It's called something special, like a Brachiohm curve, or I forget the name of it. That's the ideal path, something like that. But it's very special. And it's not a trivial thing to calculate. Whatever. I'm not going to ask you that. Don't worry about it. Okay, what I do want to ask, two spheres of the same mass are rotating at the same angular velocity. If sphere 1 has half the radius of sphere 2, how do the rotational kinetic energies compare? And be very careful here. I did something a little different than previous. The answers here are, how does the kinetic energy of 1, how does that equal the kinetic energy of the second? The order here matters. You'll see what I mean when you get your answers. So, see what makes sense. Yeah?
Is it supposed to be 5 over 2? I thought it was 2.
Yeah, it is 2 or 5. Didn't even catch that. Good news, doesn't matter. But you are correct that it should be 2 over 5. Good news, it won't change your answer. So, if sphere 1 has half the radius of sphere 2, how do their rotational kinetic energies compare? Does the rotational kinetic energy of the first one have a fourth? The rotational kinetic energy of 2, does it have half the energy of 2? Does it have double the energy of 2? Does it have 4 times the energy of 2? And because I like you all so much, here's the equation for rotational kinetic energy. 1/2 I omega squared. What happens to the energy if you have half the radius? Is it more? Is it less? What a good question. If they're rotating at the same angular velocity. Very, very important to know that. Yeah.
The clever question.
Well, you can't answer. We all have had, this was just thinking time. All right, y'all got lots of good thinking time. Hopefully you have an answer ready. I'll give you all. We'll see how quick the responses come in before I gauge the time. But be very, very careful, y'all. These answers say, how does the kinetic energy of the first one equals what of the second? Is it bigger than the second, or is it smaller than the second? Your reference is not the first one, it's the second one. Your second is serving as the reference in this setup. Because that's how the answers are portrayed. Alright, so we'll go to like 120. We'll close it out in 5, 4, 3, 2, 1. So, anytime we do these problems, they all could be solved with this recipe. Write the equation with the thing you want in terms of the thing that changes. So in this case, the rotational energy is 1/2 times 2/5 mr squared times omega squared. Now, what's very important here that's slightly different than all the other ones I've asked you. Normally I ask you, how does 2 compare to 1? This one I'm asking you, how does 1 compare to 2? How does 1 compare to 2? Is it 2 times 2, like the second object? Is it 4 times the second object? So your reference is the one you're comparing to. So actually, let's set that as our reference. We're going to use that as our reference. That is our OG. And we're going to see what happens to it when I half it. So the kinetic energy, the rotational kinetic energy of 1 is going to be the exact same as for 2, but my radius is half. It's the exact same, but my radius is half. And so once you put in that change, pull that to the front. So 1/2 squared. So everything stays the same. 2/5 m. What's 1/2 squared? It's 1/4. Pull that 1/4 all the way to the front. We want this to look like this with a number in front. That's the goal. We want that one to look like the other one with the number in front. So if you pull that 1/4 to the front, we get 1/2 times 2/5 mr squared omega squared, which these two things are the same. Therefore, the kinetic energy of the first object is 1/4 the kinetic energy of the second object. Yeah.
I think you switched those.
So because we have to get our answer in that form. I have to get my answer of the kinetic energy of the first object equals a number times the kinetic energy of the second object. That's the only options here. Traditionally, I've given you all problems where it says the second object equals a number times the first.
I'm saying in the first line, you started with the number 2. And
Yeah, that was purposeful because that's my reference. My reference is object 2 in this. Because object 1 is in terms of object 2. Previously, it was the other way around. Yeah. And also the way to think about this, what answer makes sense? As radius goes down, kinetic energy goes down. As radius goes up, the kinetic energy goes up. So if object 1 has half the radius, it's going to have less energy. You can also think about what makes sense. and see if your answer, remember that's always the last step, y'all haven't mentioned that in a while. Make sure your answer makes sense. If it doesn't, either your understanding is wrong or your answer is wrong, something is wrong. So there you go, y'all. Half the radius, 1/4 the energy. Given everything else being the same.
I forgot to bring my clicker today.
Just shoot me an email, you're good. Yeah, shoot me an email and I'll fix it.
What do you want me to say?